Hi, everyone. I'm so excited to be here. Actually, I feel like talking about all this interdisciplinary stuff, our work is a key example of how that works. It's a perfect example of both the interdisciplinary success of our college, but also how the Swartz Center for Entrepreneurship really can propel students to take charge of their projects and bring their research into real-world applications. And so today, I'm going to be telling you about how we at Impact Proteomics are enabling discovery with innovative protein sample preparation tools. So proteins are these amazing nanomachines of the cell that do all the jobs that keep us alive. And there are millions of them. And they all do different things. And when you get a disease, most of the time, it's because one of those proteins stops doing its job. And that's why proteins are the most common drug target. And that's also why we use them for biomarkers and diagnostic tools. Because even though your DNA can kind of tell you if you have a probability of getting a disease, it can't really tell you if you have it or not. And whether your proteins are functioning correctly is a concrete way to say whether they are or aren't. And when we look for new drug targets and biomarkers, you can think of it a lot like a find the difference game, where we're looking at healthy proteins and proteins from a disease situation and trying to see what's changing between the two. And when you're looking at this picture at first, it can be really complicated. Maybe the differences aren't really obvious at first. But through discovery and validation and clinical testing, we can kind of simplify this picture until the differences are really obvious. And this is exactly what we try to do. However, this is a really idealized example. And when we actually do drug target and biomarker discovery, it looks a lot more like this, where most of the information isn't even there, and the information that is there looks really bad. It's really muddy and hard to figure out. So if you wanted to find those differences, I mean, in some cases, it's literally impossible. And so another way to look at this is, we have these funnels where we start off with about 10,000 proteins, and over time, we find candidates, and we whittle it down to maybe one or two that are real, true targets. But most of the time, we end up with nothing. And that's because, remember, I told you there are millions of proteins in the cells, not 10,000. So there's this huge piece of information that we're completely missing. And the probability that what you're looking for is in that very small 10,000 is slim to none. Most likely, it's over here. And so this is a huge problem. This is why drug discovery, biomarker discovery, it usually takes 3 to 10 years, $4 to $30 million, and you have a 0.1% probability that you're going to find something real. Imagine going to Vegas with those odds. I wouldn't even bet $10 that I was going to get something. But this is why drugs are so expensive, because it takes 30 projects to get one product to market. So you have to make up all the money from all those failed projects with the money from the successful one. So really the key to making this process better starts at the top of the funnel. How can we really get all 1 million of those proteins? And how can we get them into a clean sample that we can analyze very simply? And so in this area is really where you're identifying the candidates. And within this phase, there are really 3 main steps: sample preparation, sample analysis, and data analysis. And while sample analysis and data analysis have had tons of innovation over the past 5 years, sample preparation is still done the same way it was done in the 70s, which is insane. And it leads to a whole slew of problems. Poor reproducibility from person to person and lab to lab. You're only getting a small subset of proteins. You're losing precious sample along the way, which you can imagine if you have a tumor from a person who had cancer and you lose that sample, that's precious material that's now going to waste. That's terrible. Most workflows are time-consuming, taking anywhere from 5 hours to 3 days. And the way you do it today is not automatable. So you have to have a team of people around the clock working to prepare samples. And as my boss likes to say, garbage in, garbage out. You start with a garbage sample, you're going to get garbage data. And that's why it's so hard for people to find actual drug targets and actual biomarkers, because what you're starting with gives you such a low probability of finding anything in the first place. But we know that standardization of sample preparation changes the world. We've seen this with DNA and RNA. There are companies out there that make their bread and butter making these kits so that you can purify DNA and RNA from the cell. And Qiagen is one of those. They're a $2.6 billion company. And we've even seen how this has transformed our own lives, where you can go online and order a 23andMe kit, and they can tell you that your earwax is wet, and maybe you can taste stuff that's bitter. That's where we're at now. And so essentially, this is what we want to do for proteins. Proteins should be just as accessible as DNA and RNA. But the difficulty is proteins are much more complex than DNA and RNA. DNA and RNA have the exact same structure and chemical composition no matter what gene you're looking at, what transcript you're looking at. They all look the same. Proteins come in all different varieties. They're different sizes. They have different surface charge, different structures. And so finding a way to purify all of the proteins in a kit is really difficult. But at Impact Proteomics, we love a challenge, and we like thinking creatively, and we like using chemistry to solve biological problems, and so that's exactly what we did. And so what we've created is a new molecule that the chemistry allows us to tag, clean, and release these proteins. And so if you start out with a mixture of cellular stuff, like say you started with a tumor sample, and you crushed it up, and you got all the information from that cell. Now you have proteins, which I'm showing here as circles, along with DNA, RNA, lipids, carbohydrates, all this junk that you need to get rid of. And so we've made this molecule that reacts very strongly with the surface charge of proteins. And it kind of pulls these proteins out of solution like a magnet. Once we've done that, this molecule can be immobilized to a solid surface. And when we've immobilized the proteins, they're now stuck in place. And so we can wash away all of the junk that we don't want. And this gives us a clean sample that we can really use for analysis. And the beauty here is that this chemical tag is reversible. So all we need to do is reverse the chemistry, and it releases the proteins into solution. So now you can recover everything that you put in. So this works with every single protein, so you can get all millions of proteins in a cell. And your final product is unmodified and ready to be used for any analytical technique. And so what we're really offering here is faster, higher quality, protein-based sample prep for any workflow. We want to ensure every workflow starts with a high-quality sample. You should be able to observe all proteins, not just a subset. We want to let people identify candidates 10 times faster with higher statistical confidence. And our ultimate goal in all of this is to accelerate time to market for high-impact therapies, drugs, and diagnostic tools. It shouldn't take 3 to 10 years. It shouldn't take $2 to $40 million. And you shouldn't have a 0.1% chance of finding something. We want better odds. And so this is the team that's going to make it happen. This is John Minden. This is his brainchild. He's a professor at Carnegie Mellon, and he's no stranger to innovation. He invented 2D difference gel electrophoresis, which was licensed by Amersham, now GE Healthcare, and it's still widely used today. He has over 20 years of proteomics experience and has been cited over 3,000 times. Very prolific career, and a very creative and fun guy. And Lenore already told you all about me, so I won't go into that. But we're really excited because we've completed our proof of concept, and we will begin, we'll begin beta testing in 2019. So we're working with 4 core facilities that run thousands of these samples in order to make sure that our technology can really address the breadth of samples that are out there, make sure that we can work with tissue samples and cell culture, no matter where they come from. We're also applying for SBIR next month, so cross your fingers that we get that so that I can graduate. And if y'all would like to ask me any questions, I have a poster back there, and I would love to talk to you. Thank you so much.